I want to give a talk on groceries in buildings for housing, and there are some problems related to that, and one of them is the noise from jack trolleys and trolleys of different type. And a jack trolley is typically it weighs from 60 to 80 kilos. It can also be electric, heavier. It's usually 4 or 6 wheels on it, and they can be nylon, pretty hard, PU, polyurethane, and the hardness varies, or it can be rubber, which is quite soft. And if you don't have the opportunity to measure their hardness, you can see the PU wheels usually have different colors. It can be red, it can be yellow, it can be brown. Rubber is almost always black. Can have colors, but then it's for lifting bumper plates and so on. But I don't think I've ever seen other color than black. The nylon for wheels. Nylon can be gray, white, or black, as we see up there. Here we see some examples of used trolleys. This is, I think it's a bread trolley, or and there's a PU outside of nylon or another type of plastic. Under there we see a typical nylon wheel, very hard usually, cheap trolleys, and often the milk trolleys or bread trolleys or meat or fish trolleys, they may have such hard wheels, and they may be even worse than the jack trolleys. And this is from a test of a resilient layer, and we also dropped an apple, and an apple is quite soft, so you need something better than a impact reduction floor surface to improve that situation. Some relations: the thickness and the hardness, Young's modulus, E, and the contact area matters. And the dynamic stiffness is the E module divided by the thickness times the contact area. And I believe the trolley is possibly like a floating floor. A mass above a springy wheels, sort of. In linear spectra, the noise maximum will come around the resonance frequency of the floors, sort of. Harder and shallower wheels will give higher resonance frequencies, and you hear it quite well. When the wheels are hard, you hear it quite well. And recently there was a PhD conducted by Edwards, I think his name is. I will come back to that. But if you pull out the numbers from the measurements, you get a correlation between rolling noise and the energy, kinetic energy. And you can split that into terms for the velocity, which is the most sensitive parameter here. The mass also matters, but it also gives, when you increase the mass, you also make the trolley softer or more insulated, so it doesn't need to be increased rolling noise. It can decrease sometimes. And a heavier trolley is more difficult to get into speed as well, and you handle it a bit more carefully, maybe. And the K there can be related to the roughness of the wheel or roughness of the floor, tile joints, irregularities of the wheels. If it's flat on one side, you get clack, 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 and so on. And then you have impacts, that's collisions. Example giving at doors or from outside to inside, or you simply drive goods into the walls or let the pallets down hard. Impacts at collisions are analog to impacts after free fall, h meters, and the velocity in the free fall is the root of 2 times gh, and the g is the gravity constant. So it's useful maybe to measure the speed of a trolley if you want to do a measurement very precisely, or at least to maximize the speed. And it's also possible to measure the hardness of the wheels with a durometer, or a meter, like the one you see here. And we will see some examples of that later. This is an extract of data from Matthew Edwards' PhD. I've copied his linear spectra, weighted them, summed them, and I have also corrected from 100 millimeter concrete floor as he used to 200 millimeters, and presented them in this semi-log plot. And it has been shared on like LinkedIn last summer, and quite a few persons have seen it. This is his test trolley. He has a flat part of the wheel there, and he can exchange the wheels and have a smooth wheel. And the flat wheel, clack, 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 is the orange curve there. And below the floor, there's about 70 decibels equivalent level as they are following a route around that floor. The maximum speed is about 1.6 meters per second, and the lowest is 0.5. And the span from the lowest speed to the highest is maybe it's about 15 decibels. And the pure rolling noise with the perfect wheel is the blue one there, and it's 15 decibels between those. And we have data for a dolly, 4-wheel nylon wheel dolly, which is there, noisier than the perfect wheel trolley. And there's another small dolly with data here, and the suitcase is down here, and the vacuum cleaner here, office chair is there, and then the 3-wheel dolly is this one, quite heavy, sort of, with the turning wheels. It's there, and with 3 points, contact points, you always have the contact with the floor, and you have 4 points. You will probably always have 3 contact points, and the fourth one, there will be some impacts there related to the contact. And then we have the orange points up there are here that only they have the same speed but change the mass. And for the shaped wheel, there's not much difference between the masses, but for the perfect wheels, the sound level goes down about 5 decibels from I think it's from 10 kilos to 30 kilos also there. So that was an example of reduction of sound level from increased mass. And one explanation for that is that you get more deflection of the wheels, and the spectrum of the trolley changes a little bit and you get lower levels. Yeah, and then we know from weight drop tests we have from different buildings that the difference, the insertion loss from floor below to the floor above can be from 9 to 20 dB, sometimes even more. But for an example, now we use 15 decibels, and we use this on the data here, sort of, and we translate the data down 15 decibels, and in Norway the limit is 27 LI max, and this is equivalent levels, so it's not directly comparable, but we get an idea anyway. And we would have too high levels above the test area here in a building, and you couldn't have this below an apartment, for instance. However, you can work with floating floors and so on to improve the situation, and we will come back to that a little bit. We will probably not be able to make it so they can work freely, but with soft wheels and so on, it might work. Here is an example of measurements done with an accelerometer with different trolleys, with hard wheels up here and soft wheels down here. And I think this is linear spectra, and the difference in overall sound level is about 30 decibels. And maybe it's a bit special here because this was a case with where they had working very hard to get improvements, and the green line there is from a trolley with Blickle wheels who supported the project with good products, and it improved the trolleys quite a bit. Yeah, and the red one is a milk trolley. The orange there is a bread trolley, old bread trolley, and then I had a new one with the crosses there, probably a good wheel, a new wheel. And meat cases are the blue ones before fix and after fix. So you can do things to the trolleys, absolutely. Here we look at the variation from the position of impact sources, and there's a bedroom here. We impact below the bedroom in the grocery store, and we see the concrete parts around, red parts, that's a slab or wall going through up to the living room or apartment above, and this is the goods reception, and the truck will back into this region here underneath a roof, and the warehouse is here, and here's a milk. It's a sort of it's a cooling room, and we see for those four positions, there's 40 to 43 there, 50 to 52, 43 to 46, 48 to 51 dBA, I guess, from the Hammer apparatus with the receiver up here. So there's about 12 decibels variation related to proximity to the bearing load-bearing constructions, and there's possibly a sort of a floating floor in this room here, giving lowest values of the all. Here we see some everyday examples. This is an old inline skate with the wheels, 80 shore A. It's fairly quiet if you roll it over the parquet or floor. And when you run it on asphalt, you feel that you can feel some shaking, but you can feel that the shaking is damped. This is a longboard. The wheels are wider, smaller in radius. 77 shore A, it's quiet when you roll it over the parquet. You can hear something when you get it up to speed. While this bench here with the 97 shore A wheels, they are quite noisy when you roll them over the parquet, but still you can push the nail somewhat into the material, so it isn't stone hard. But the correlation is quite clear. If the wheels are hard, it will be more noisy. Now this is a trolley, local trolley, not far from our cellar room in our office building, and this is probably PU 97 shore A, both in front and the rear wheels, and they have been used for a while, and I take it for a ride here. The bump doesn't have brakes, so there's been a lot of bumps there along the wall there, and it doesn't have brakes, so it's something that inevitable will happen, and a floating floor won't protect against that impact. So yeah, here we have some data from Portugal. It's a study by Mateus et al. It's a group of persons. They've measured 60 impact levels from below and up to rooms above, and done it very systematically so that you can run statistics on it. And the most important parameter in that data set is the length of the common plank wall, and it's quite high correlation there, and we will come back to multiple regression on the data because we have more correlations. This is the volume of the reception rooms, quite small rooms, below 50. Some are also below 40, most below 40 cubic meters, and that's smaller rooms than what we are used to in Norway, where we can have kitchen and living room in the same, and quite often we see over 100 cubic meters when we do impact measurements or sound insulation measurements. And here we see the second parameter that is significant quite weak, but it's still there, and it makes sense that the surface mass of the floor you tap influences the resulting impact level in the floor above. And the mid thickness, if you do the calculation here, is 170 millimeters in the study, so it's thinner than what we usually see in buildings in Norway. Seldom under 200 millimeters. 250 and 300 is more common in the first floor. Here is the regression, multiple regression formula. We still see that the length of the common flanking is important, and the effect of the mass. And it explains about 60% of the variation in the data set, which is not bad. Here are the spectra from the study. They have divided it into the highest levels, above 56 decibels, and then they have a mid range from 52 to 56, and then a low range. And we see a comparison with an average of about 30 measurements we have done in Norway, and the shape of the curve is somewhat similar. It's a level difference there, which may be related to stiffer, heavier floors and less wall slabs maybe. It's only one study, one column supported building in the 60 and 60 data set from Portugal. They also use brick walls, light brick walls, and inner walls of brick. So it can be related also to the build type of buildings and the way of building in Portugal versus in the northern in Scandinavia. And what we see up here is the average of many 200 to 250 concrete slabs in field, and that's below, and then from above to below. And if you parallel move that down to the impact levels spectra measured from below, you get a gap there, which I think is related to propagation loss. You have a geometrical loss, which is largest close to the sources, and then when you pass about 10 meters or 5 meters, if the losses are high, you start to see effects of the propagation loss, and it will be larger for the highest frequencies. It can be other factors as well, but that's one of the contributions to that. And the effect is the important thing here. You get a floor that is less receptible, sort of, to, you don't get, I will come back to that, you don't get the full effect of impact reduction means in the floor below, because you have this shape. And this is what I will come back to here. And in Matteus' study with floor coverings and up to a floating screed up here, the impact level improvement from the laboratory is the number here, and when you put that on the spectra measured above, you get 21 for 24, or similar 17 for 24, yeah, so on. And it depends a little bit on the level of the overall level of the impact on the, before you put something on the floor. and it's about 3 to 8 decibels difference there. Here I have done a similar calculation, except that you have the impact level improvements along the x-axis, and then we have the LA maximum levels from trolley spectra along the y-axis, and you see that the numbers for the trolley improvement insertion loss is lower than the impact improvement numbers, and it's quite a much lower, 12 to 14 decibels. Some solutions are a little better, but they are part of these calculations are theoretical, so we only have the low frequencies, okay, but it could also be the fact that very, very low resonance frequencies will tend to make the changes above 100 hertz very small. So yeah, and this is direct casted concrete on. So yeah, that's the numbers. You get less out of the floors than you would think, and that's important. Here we see the Portuguese data along with the surface mass here, and then the impact levels along there, and then we have our bare floors measurements upwards are those orange data, and then we have with floating floors those green, and we have some data here indicating not so well functioning floating floors. Here we have some effect, I think, but not all that much actually. It's also a measurement problem when you start to measure impact levels below 35 decibels or 30 decibels. It will often be background noise limiting the possible measurements. So, and it's also so with trolley measurements, sort of you have information in a few 1/3 octave bands when you're low here. So there's some challenges also with the measurements. And this is a theoretical line for impact sound level from above, and it has a steeper curve than we see in the data. And on to the right here, you see the jack trolleys, and again we see the massive bare floors to the right, and the weight of the floating floor is lower, and they're here. And again, you can see some effect, but it's not all that fantastic. Then we compare the jack trolley measurements to impact 40 kilos drop down bare concrete and measured above or calculated above, and it's not natural to have a situation like that. So you can if you reduce the levels by about 30 or 20 decibels, about what you get out of a 20 millimeter mat, you get the numbers down to this more or less the same or the same range as the trolley levels. And many people in multi-use buildings might live under such conditions. And It's okay if you don't get this before you wake up in the morning. Or okay, we should have been down to the red line there, but that will take more than just a mat, and it will take more than a regular floating floor. Here we compare the spectra from a loaded and an unloaded jack trolley, and the spectra from weight drop, and they are similar. And here we have a 15 millimeter mat, dropped it on a 50 millimeter mat, so somewhere between the hard and the soft, we have a spectrum similar to the jack trolley, and this might open up for measurement solutions, or you have at least you have enough signal from the dropped weight, so you can measure longer distances than just to the next floor. And here we compare, we wonder, can measured impact level predict the jack trolley LMX levels? And to some extent, there is a correlation, but for low levels, there is a tendency for the jack trolley or trolley noise to be louder than the impact level, and at high impact levels, they are more similar. And the reason why the trolley noise is higher, might be higher, even though the impact level is low, is that you have also noise from passing doors, changes in the level of the floors, bumping into doors or even walls, and so on. Other factors than just direct trolley noise. And there's a large variation, as we have seen as well. And to some extent, we do not know why it's like this, but we try to explain as best as we can. Here I have compared impact levels and equivalent levels. I weighted the impact levels to see how they compare, because sometimes you will use the impact hammer as a guide to figure out where do you have more impact sound coming from, and so on. And in general, for hard surfaces, the equivalent level tends to be higher than the impact sound level, and for softer floor coverings, they are more similar. And we have used, that's it, and it's about 5 decibels difference between the equivalent level and the LNV. I think it must be different. It must be minus. It's higher for the LAAQ, so the formula down there is not correct. It's also a problem for many that the trucks arrive very early. They want to come before the morning rush, and it's usually several trucks. It's one for dry goods, things you can store for a long time, and then you have short-term, like milk and meat, fish, and so on. And then sometimes they will come with liquor, beer, and so on in one delivery, and bread and bakery and such stuff. The cooling goods might have a noisy chiller on the cooling trucks, will have noisy chillers on the roof. It can be noisy. And there's a back alarm sound system maybe. maybe air release from the brakes, high levels through windows and facades, noise from goods handling on the truck, ramp and in the building. And noise on the truck is bassy, because you have thin constructions with heavy loads on. So, and here we see a noise power histogram with 16 happenings an hour at 93. You have 11 at 97 and 3 at 103. This is from this situation, and it's building housing on the other side of this fence. It's not the main part of this task, but certainly this matters for a person with a window and facade against goods delivery. There are some requirements for point load in groceries. One boutique, large boutique in Norway center chain uses 20 kilonewton per 0.2 square, and that's about 750 kilopascal. And the construction engineers wants 220 millimeter reinforced concrete on 200 millimeter XPS, and that's pretty stiff. And he says it's not possible with traditional resilient layers like mineral wool under the concrete nor under the XPS. And these are more of the requirements. And this is about 1.5 ton weight and is 3 ton weight. It's almost like a car. It can be steel, shelves with long distance between the feet and quite heavy goods on that. So under those feet you can get quite heavy weight, and you have the trolleys, and they can lift more than 1 ton, but it's difficult to deal with them then. But you share the weight on 4 or 6 wheels, and if it's electric, it might be more, I think. And they also weaken the floating floor by making cuts in it to guide the cracks. And in this situation, there's about 6 meters between here, and it's a 6 by 6 or something like that. So if you put a high pressure on it on a floor like that, you would probably have to make it even thicker to function well if you have a soft material under. And here we see compressional strength of dwelling house solutions, and usually EPS they are 4 to 5 kilopascal. Given numbers and measured numbers are higher, but you have to take into account the weight of the floor slab or the concrete or screed on top of the material. In addition, the material shall also be able to withstand and keep its properties if it becomes wet and so on. So there's margins, and here we see some numbers for some common resilient layers used in Norway, and those numbers are quite low. And here we have looked at some layers. This is rock wool, 235 kilo per cubic meters. It's a very dense material and stiff material, and its compressional strength is about 70 to 110, depending on the thickness. The thinner it is, the more load it can take, and the dynamic stiffness is quite high, 90 to 100. And then we have, this is ballast nuts used in under railways and so on. Usually, we also have some EPS of different types. You can get them from in a very wide range, and the lowest and the highest range here are the dynamic stiffness for them, and similar for XPS. And it's possible to do calculations on this. The compressional strength and the dynamic stiffness follows closely the density. So it makes sense to know the density of the material. It doesn't necessarily pass across the different material types, but within the material types, this makes sense. And the contact stiffness is more important for stiffer sheets. That is, when you lay out EPS or XPS on a floor slab, you don't do anything to fix it to the floor below. It's just laid out and you put a mass over it, and the contact won't be 100% under there, so you must account for that in some direction, some sense. And here is an example of calculated effect of this is a trolley, jack trolley noise in the floor above from on vinyl, thin, stiff vinyl, and then we put a floor as the construction engineer wished to have with 200 millimeter XPS 750, and we get 3 decibel higher noise levels. And if we look at our original suggestion, 50 millimeter rock wool with the 100 millimeter concrete on it, that would give about minus 9 decibels from the jack trolley, and that achieved to prove it is quite realistic. But I think that the levels around the resonances here are a little bit exaggerated. It is a vibration insulation model, assuming a single mass and a spring, and the floor is more complicated than that with I've learned that it is a waveguide, and the resonances in the floating floor plate will collect around the floor resonance, and then you have a very complex situation there, and it's certainly more complex than just a mass and a spring. So it might be more rounded, and maybe I've used too low damping as well. I don't know, but you don't get much help from that XPS floor, and it may even make the situation worse. So that's a dilemma. This is calculated insertion loss from I use middle spectrum for trolley noise, and let the bare floating floors impact zone insulation meet that spectrum, and then I see what will the difference be from the original spectrum to the spectrum from on the floating floor. And we see that the thickness of the floating floor is the x-axis, and the y-axis is the insertion loss of the floor. And we have several different types of floors in here. There's some very special spring supported floors, spring supported floor. These are gym floors, very special. This is calculations this is partly measurements and partly calculations. And then we come down to kinetics, point supported floors here. This is also kinetics measured by us. That's a kinetics kip floor with glass fiber cubes, and we have some ground-up floors with concrete tiles, and different traditional floating floors. This is a poor workmanship version of it. This is direct casting, a thin type, and this is screed, floating screed on EPS. So 8 and 10, and then we have Getzner acoustic floor mat, gym floors, and this is also Getzner G-fit impact floors with waffle mats, I think, and the screed. So not many are above 20 decibels, and some are down to almost just above 10 decibels only, and even worse. And this is an attempt to do calculations. And there's beton, that's concrete. There's one 4-meter concrete slab here, and I've made what we do is to make calculate the impact level from below to above by calculating from above to below with a very good ceiling, 50 decibels flat, and I have on top of the floor I've added a surface as if simulating that the propagation loss, and you can change the surface of the concrete here to simulate the floor below, because you don't have the floor there included. And I get with the 300 millimeter concrete floor, I get 44 impact level, and the regression model gives 52, which is 8 decibels conservative, and they are clearly lying above our measurements. So and here we see our measurements again with the impact levels. This is the Portuguese study, and the calculations are the lighter color there with no correlation for the propagation loss. So and there's another curve down there. I don't remember what I did for that situation, but with the amendment with the propagation loss, we get this curve, which sort of lies in the above region or higher region of the measurements. It could have been higher, but I haven't tweaked this much. And down here we see the calculation from a very good 100 millimeter concrete floor on 100 millimeter mineral wool, soft mineral wool, and if we distribute it together with the measurements, I have these rings here, and they are in the same ballpark. So it's sort of possible to do calculations, at least on a tweaking level. And the conclusions: none of the measured buildings are meeting the limit values of LI max, so 27 decibels, and that's the limit for service noise in service activities in dwelling buildings for dwelling. It's stricter for the service activity than it is inside the dwellings, then it's 32. The relation between impact level and LA max from trolleys is significant, but 65% of the variation in the trolley noise measurements lack explanation. So it's other factors influencing as well. It's not only the floors influencing. We can calculate the impact level up in Bastion with some tweaks. Groceries has to adapt to the building, no matter choice of floor solutions. They have to choose, possibly choose or limits to the time they can be active in the building, type of wheels, soft wheels, the layout of the plant solutions. You shouldn't have sleeping rooms, apartments near the goods delivery. Use the distance loss and geometric loss and propagation loss. Yeah, and with 300 millimeter massive concrete, we can get under 48 decibels impact levels, which is the limit for service in Norway. Not by far good enough for groceries, but for general situation, it might be okay. And I say, given a column supported building, if it's slab supported, with slabs going through the apartment above, forget it. You won't meet that requirement. If the compression strength requirements makes it impossible to have good resilient solutions at the floors, groceries cannot establish in the same building as apartments. And this is maybe new information to most consultants. And question here, if you count the number of events above limit value, that might be useful. When it's worse or a bad situation, you can have 300 events above the limit in an hour. Difficult if you're sleeping, trying to sleep. So I wonder, where is the limit? Could you live with, is 10 events per hour okay? Can you smear that out over the day? Or where do you think the limit should go? I don't know the answer, but maybe we have some experience that can explain this, and it will also be valuable for gyms in the same building as apartments. Okay, thank you for now.